Okay.
Okay.
While Professor Billard is sharing her screen, I will give a short introduction to her, if I may. So Professor Aude Billard is a full professor at EPFL and an HPE fellow. She has received multiple awards in robotics and machine learning. And she is a world-renowned expert in the control and design of robotic systems meant to interact with humans. And personally, I have been very inspired by her research and talks. So for example, when I was a PhD student at King's College London, so I still remember in this big classroom we were attending her inspiring talk.
That's very kind of you, Shan. You may be the... I'm sorry?
It is our honor to have you in our workshop. Thank you.
Thank you. Thank you for the invitation. It's very kind. So today I will not talk at all about what Shan saw in that particular talk where I did present the work that we do on, funny things like catching objects in flight and left and right. Here it's going to be much more focused on tactile information. And I immediately want to apologize to all the people who came and wanted to see talks about visual and tactile information, because as I explained to Shan, we actually assume that the robot is blind, and so we look only at tactile information. And in that respect, I think it's a very limited work, but I mean, maybe it can be combined with the recent progress that have been made in this visual tactile learning, which I look forward to hear in the other talks. So with this, I hope you can see my slides.
Yes.
Yeah. Okay. So this is a faked image, and I like to show it because I hope one day it won't be fake. In the sense, it's a real human hand, it's a real robot hand, it's the iCub hand, but the human is not fake. It's actually holding these objects. The iCub is holding them, but because we put the two objects into the fingers, we don't yet have dexterous grasp that allow you to pick up objects with multiple fingers, although we're coming to that slowly, and we'll probably have a paper this year on that, but it's still very limited. And the reason for that is that most of the work that we have in robotics do have tactile information only at the fingertip. And if you want to be able to hold object like this, you need to have tactile information along the entire length of the finger. So for quite some time, we have worked on getting this on the entire length and getting this information. But yes, I wanted just to bring this up because that's what we're lacking. We're lacking to have enough tactile information and also joint angle that will allow us to pick up this object and apply some residual force on the sides. So I'll show just one video where we started doing that today, and unfortunately I can only tell you that it's going to come up in a year from now. The very first thing that we did that was jointly with Metin City was to see if we could augment and have a combination of both tactile sensing, as you see here, and adhesive, in order to be able to pick up things that are very flat, where you have no grip. And so this is a nice example where you can detect you have both touched and also the object is actually adhering to the surface that you're sticking on. And then you have to use the second finger to take it out. But such a simple mechanism where you just combine tactile sensors with adhesive allows you to have fairly dexterous motion without much cleverness. And here is another example. You pick up with one adhesive on one finger, and then you use the other two fingers to rebalance the force with the tactile sensor. We then moved on to doing compliant control based on tactile sensing, still looking at a very simple control mechanism. Here we're just changing for the impedance at runtime based on the tactile response, and allows you to have a very safe and compliant mechanism to scan surfaces. And we use that for funny things such as recognizing different faces, still with this idea that if our robots are blind, then we better do that as blind people. That means to be able to recognize surfaces from this tactile sensor. So what we had was different model of faces, and what you see here is the actual model recognizing the different face as you scan them. So we scanned these different faces. We created a temporal model of how the shape will unfold under our fingers. And at runtime, we can have the model that detects which of these four, or these 4 different faces it's scanning, and it was fairly accurate. So really simple. Then we move to looking at how can we use then this tactile information in a coordinated manner, and use machine learning as a way to retrieve some information about the stability of the system. And something that I've been very eager to see in robotics at large is to move away from what we call optimal control, but look more at feasible control. What is the feasible space of posture, for instance, for that robot, such that it doesn't drop this can. So usually when you use optimal control, as we are doing here, you want always the object to be at the place which is the most stable one. And if I have a very stiff controller, then as soon as someone generates a perturbation, as we see here, pull me away from this stable position, then I will get back to that. And you know, the optimal posture, which is the one that center is making sure that the center of mass is roughly within the polygon. The polygon of stability is the best, and based on tactile sensing, all of that is not that great, because I mean, often what you want is more to know to which extent can I move the finger, and here is an example. To which extent can I move the finger around, and this is still stable. And there are lots of different posture. Of course, there are the posture sideways, if you don't want to drop the liquid inside. And then you have a posture also, you can also rotate to some extent. So what we did was to teach the robots this range of posture, and to look at the tactile map at the fingertip that we get here, and to learn our relationship between the different postures. We have the joint space on the finger, and the tactile signature, which is decomposed into the normal, that's just a sum over the pixel here, and the actual map of the tactile information, as we have seen before. So when you try to learn a mapping between these, it becomes a very high dimensional map. In this particular case, it was 42 dimensional. And once you have this map, which you can learn with many different machine learning techniques, I think Shan mentioned one of them. So what one can use, we did, I think, very similar to what Shan presented, the learning with a mixture of Gauss function. It's a density-based approach. You get this probability density representation. And the good thing is that when you have a probability density representation over the joint angle here, the tactile signature, the normal, as well as the full map of the tactile signature, then at runtime you can query for any of them. So let's say that you move the object, so the joint posture have changed, and you have a new tactile information. You may want to query what is the best representation, the best joint posture that will ensure that it's stable. So and you may force the system to always go back to the stable posture. So when you have this manifold, which I represent in 3D because I cannot represent 42 dimension, all the points that are within this manifold here are stable. All the points outside that are unstable. So what we can do is if at runtime you push the object away from the initial location, the robot will accept and will retrieve a posture and stabilize, also apply the right amount of force to stabilize the object as long as you're within this region. And it may become stiff as soon as you want to exceed this region. So there are some rotation that will not be allowed and other that will be accepted. So this was the first work that we looked at on this, and we showed that we could extend that. So here is another example. You can hold this object at the fingertips, still with a simple stable control. Then show to the robots that you can turn the fingers, show more rotation and position. The robot is not observing anything. It's really purely tactile. It gets this dispersion of tactile information at the fingertip. This dispersion of posture at the fingertip learns a mapping between these two. And then at one time after that, you can query the system for different posture. And what I like in this work is that also it changes automatically from sometimes holding with 2 fingers and sometimes holding with all 3 fingers in direct contact, even though this was not. After that, we spent quite some time looking at other things. So this is more recent work to look at how we could then use this tactile information to adapt to change in weight without knowing necessarily what's the shape of the object and what's the amount of weight. So taking still a machine learning approach, we trained the system with different distribution of weight and different shapes. And there we learned the stiffness to be applied. We represented things in the object frame of reference, so I will not spend too much time explaining that, but basically we learned a probability density function this time on stiffness, on sort of a notion of spring to the center of mass and the force that are applied at the fingertip. So it's a bit the similar system, and we learn a distribution of force at the fingertip, a distribution of stiffness by how much we need to stiffen up to not drop the object, and where the center of mass is. You learn this, again, from the tactile signature. You don't observe the object. All you have at your disposal is this notion that the tactile signature changes, and if it does change, then that means that there is some change that is happening at the level of the mass distribution within the object. And this is true for many different objects. In fact, you don't need necessarily to observe the shape, because this tactile signature will probably be very similar and will be indicative of this change of the mass of the system, this relative location. So you can learn that. It's even higher dimensional than what I mentioned before. Here, what I represent is a slice when we do, for instance, PCA on this high dimensional space, so that you can appreciate also how non-convex this representation of the feasible and stable posture is. It's clear that it's very different from the previous case, because now we're also changing the mass distribution. So there are much fewer position of the finger and tactile representation that are feasible and still stable. And once you have that, then at runtime, you can query for change of the stiffness. So for instance, if typically the mass increases and the distribution of mass increases, then what the system will automatically detect is possibly that the stiffness needs to be changed. It may also detect that it's not just the stiffness, but it's actually the posture of the finger, or one of the finger that needs to stiffen. And this is done automatically. It's not as if we decide that, okay, this finger is slipping and this other finger is slipping, and now I should control for it. It's actually coming directly from the distribution. So each of the finger needs to be within the manifold of feasible tactile joint signature. And if it isn't, then it's changing the position. And we also, as you could just see in this video, we also retained this nice adaptation of the displacement of the object. So we have both stiffness increase now at level of all the fingertips, or one at a time, depending on how we're doing. And then we also have the adaptation to perturbation, in the sense that if you displace the object, like here, I'm making it slip, then you will detect that the tactile signature is now is not within the manifold of feasible posture. And so one solution is to increase the stiffness, another one is to move the fingertip. As I mentioned in introduction, I'm fascinated by the fact that we do have tactile signature in the entire length of the finger, and I've been striving to try to get this along the entire length of the finger of the robot, and to use this, of course, for stabilizing. So the first thing that we looked at was to have this tactile signature along the entire length to allow us to better scan. So to get this 3D point cloud from scanning objects, as you see here. So that's quite useful, and in fact, there are many other works who did the same thing. So it's really nice, that way of doing it, and I very much like what Shan presented before, to combine also with visual information without directly making contact. And then another thing that we then moved to was to say, well, okay, we can do this tactile signature, that's nice, but reality is often that our robots are very limited in the workspace. So here I'm departing slightly from tactile information to just talk to you about control, which is something that we do more in the lab. But what we wanted was that the robot could actually scan this very complex object, and scan the entirety. And as you can see, because the workspace of the robot, the bimanual workspace of the robot is limited, what the robot needs to do is to always move the two arms in coordination to give more room for one arm to scan and to rotate the object to search for it. So I'll just explain very briefly how we did that, even though it's departing a little bit from tactile information. But I think it's useful also in the context that if you want to use tactile information to scan, and imagine you want to scan your own body, then at some point you need also to coordinate the entire motion of the limbs to allow for this scanning to happen. So to do that, what we did was to have a representation which is similar to what I said before about tactile signature and joint signature, is that we had a representation of the workspace of the robot arm, the left arm and the right arm, and then the bimanual workspace, which in practice for this beautiful robot, the iCub that you see here, is actually very, very tiny. So there are very few places where the two arms can reach each other, not to mention even fewer space when you have an object in between. That creates an obstacle. So once we have this bimanual workspace, what we can do is at runtime decide, okay, there are regions highlighted here in red that I haven't scanned yet. How can I get there? And then you need the two arms to jointly coordinate their motion to help the one arm to generate this, to make the object meet the other arm within the workspace. So that's just a funny video that I wanted to show to you, because just to say that our robots are blind, we actually put glasses to showcase that the robot is blind, just to illustrate the fact that we did not have actual visual scanning here, except for the fact that we're actually tracking the position of the arm, so it's proprioception, and here we're tracking it with external camera for precision. So with this, we could build different tactile signature for complex objects, move them. One thing we combined there was what I showed before, was this notion of compliant control as you scan, which is based essentially to change the impedance at runtime between the tactile information that is provided by the finger and the posture, such that you can really scan objects, even if you don't know them like this, and you can scan them relatively precisely and smoothly. Another thing that we then did on top of this was that once, I mean, we thought, okay, if you have a manifold of the object representation that you can get from this tactile signature, could you then use this to do more than just increasing the stiffness or slightly moving, repositioning the finger? Could you actually have fingers jump into a region that are feasible? And so that's quite complex in effect, because to jump, you need to really have a representation that is fairly accurate of where you can jump with the finger and how you can restabilize. So once we had this tactile signature of the object shape, we could, I mean, it was a closed form representation, so it was also C1, so you could derive the normals and compute the normals to determine the contact point at runtime. I assume that you have a 3 fingertip in contact with your object, and that your object is subjected to a perturbation, similar to what I've shown before. What you need is to be able to restabilize that. So to restabilize it, sometimes just increasing the stiffness or moving slightly the finger will not do. And if you really want the object not to fall, you may have to jump. And to jump, that means to really go from one point to the next. So to do that, you can, once you have this representation of the manifold, there is a fairly easy way to do that, is to move along the tangents to the manifold. So you can either slide like this, if you can afford it, if you have the time to slide, and if you're sure when you're sliding that you're not generating more torque and you're not really going to rebalance. But best is to actually jump like this, okay? And to be sure that you can do it fast enough. So we took the second avenue and to actually jump on the object. And so you have here examples that are based on the combination of what I presented before. So you have a model of what are the feasible posture, joint posture for stabilizing the object. You have a model of the tactile signature. As soon as the object is off balance, then because you have this model of the shape of the object, you can decide to jump to another location, which is feasible within your workspace of joint position that are stable. And this was learned on different objects, and we could show that it was actually learned on the small bottle that you've seen before, and we could show that it will actually extend also to larger objects. So it wasn't just constrained to a small shape. It could also enlarge. It could also generalize to a larger shape. Further to that, to really exploit again this entire tactile signature on the finger, we looked at how we could maximize the contact at runtime. And one option to do that is when you're still blind and you don't have any information of the shape of your object, is that as soon as you make a contact with the object, is to decide, okay, how could I now try to put my entire hand on the object to get as much information as possible? So we took the opportunity to think, okay, let's say I make a first contact and I get the normal to the surface, which I can easily do with most tactile sensors. I get that, and I assume possibly that locally at least the shape of the object is convex. If so, then the other joint of my hand, my finger, just have to then move in the direction to align to the convexity, the local convexity. So I can move in the direction that is highlighted here in green, which is combining both the direction of the joint space and the direction given by the normal. So if I do that, then I can have an easy way in which I, here I hold onto the object, I make a first contact and up, I maximize the contact. Same here, I can flatten, see, makes contact with the last phalanx and the top phalanx, and then forces the middle one to also make a contact, which is quite natural. It's something that you will do yourself. And here is another example, and it allows you to also come closer and then scan with the entire length of your finger this particular. This also can be used to go just one step closer to the first image that I showed in the introduction, is to start also holding an object with groups of finger. So how do we solve for that? I'll give you just a little bit of an idea of how we can do that. Like I said, the concept would be, as soon as you make a contact, you assume local convexity, and then you will try to move towards that. But you have to move all the joints while keeping the contact that you already have with the object. You have a set of desired contact, and you want now to make other contacts. And these other contacts, you like to make sure that they're stable. So you can solve this. You can first generate and compute all the torques that you have to generate on every single of the finger, and then you can solve with a null space projection. It's a null space projection based on your definition of the desired contact. These are the first contacts that you already have with the object that you don't want to lose, and secondary contacts, which are the ones that you hope to get by moving towards this convex shape. And once you have that, you can at runtime really run it relatively fast, especially in simulation, and then use this to maximize all the contacts as you scan a completely unknown object, as we see here, and use this to reconstruct the shape of the object, complex shape. Interestingly, also in simulation is that you can start looking at having contacts not inside just the finger as shown before, but also on the outer side of the finger, which I haven't seen often enough, and I really hope to see more of this to scan inside objects, because this is so useful, and often we don't have information of the inside of the object. In fact, visual information often gives us only the outside of the object, because that's what we see from the outside. And tactile information can complement that. So this is also a nice way in which we can maximize the contact. Just let me play this once more. Observe that the hand goes down, makes contact, which are the green point. As soon as it makes contact just at the fingertip, now reverse side, then the hand falls down, falls forward, and then maximize the contact now with the outer part of the finger. So this null space control works in both ways. It doesn't force the system to make contact with the inside of the hand. You could also do it with the outside of the hand, and also with the side of the fingers, as I showed before. This was then combined with grasping. So you close on the finger, you maximize the contact, and you also, on top of that, search for places where the object will be stabilized, meaning that for this we need to compute the balancing. So we need to compute at runtime the change in the force and to see that it's actually balancing. And this was used to hold a different object and to show that at runtime you can hold this object and then perturb it. And even if it's a complex object, the finger will actually adapt to the change in the positioning. the entire distribution of the finger. And lastly, that's more recent work. We started collaborating with people who are interested in using EMG control to control for the finger of the hand of the robot in order to control for prosthesis. Here is the work that is done by our colleague Silvestro Mechera, who is capable of detecting the EMG for every single finger. It's very useful for future prosthesis where you will control each of the hands separately. But one problem, of course, with the control system is that from time to time, the EMG is poorly decoded. And that will happen probably always also because it requires quite a lot of control from the patient's viewpoint. So we started collaborating by saying, look, we can still detect with EMG the contact, the motion of the finger, which we see here, to close on an object. But because it's going to be imprecise, and from time to time, what will happen is that some of the finger will reopen, as we see here, even though the hand is closed. And if we combine this with our control system that enforce that as soon as we make a contact, we maximize the contact in the finger and we hold stiffly the object, then we have a better chance to not drop the object. And we did a systematic assessment for that. So this is again here the example of this individual finger EMG control system done with the system that Silvestro Mechera developed to hold and move an object. What happens in practice, even though it's really a fantastic system, it will drop the objects quite frequently. If you use the shared control, we could quantify that really over several subjects, several experiments. If you do combine this with this automatic stabilization, maximizing of the contact, then you actually make sure that the object is not dropping from the finger. And you have much more accurate control. And also it decreases the amount of, let's say, cognitive loads that you ask from the subject to control swiftly the EMG. Now, this is the most recent work that we are doing, and it's just a tiny step to go to use vision in conjunction with tactile information. So we do have a standard network controller to detect different objects, okay, that we can detect with a gaze camera on top of the forehead of the person. And now we've started to combine this to enable the robot here to be controlled both by the EMG, but also controlled with vision to place objects and to also rotate and insert objects into each other. It's very, very preliminary work, and so there will be more, I hope, in the year that comes. I just wanted to briefly touch upon another work that I thought maybe you may find fun, which we presented at ICRA last year. That was sponsored by Samsung. They were interested in developing a robot to do massage. And this is an example of the massage they were interested by. This is a typical arm massage where you massage with your thumb. And clearly what matters is the contact, is the pressure that you apply, the maximizing of the contact for sure, and also the amount of pressure. If I play it once more, what you probably observe if you pay attention is that clearly the person presses more as she goes inside the arm and then presses less and so forth. So we had a few therapists, we had one therapist coming a few sessions in the lab. We recorded the motion of her finger as well as the tactile information. I'm not showing that here, but we had tactile sensors to record that. And we measured the change in the tactile information. Now we could learn the relationship between the movement and the force that was exerted in terms of the pressure on the finger, and model this as this is something that we do in the lab a lot, is to model this as a quiz of linear system and limit cycle. I will not discuss that too much, but it allows you to embed quite nicely this profile of transition, linear transition, as well as the little rotation on it. And also, most importantly, that we could embed now along to this representation of the motion, this notion of the change in the tactile signature. So this is re-represented here. We have a way to model this transition in space, and then we can also model the limit cycle. And on the limit cycle, we can also model a limit cycle in force. That means that you increase the force, decrease it, increase the force, decrease it. And we model the increase and decrease of the force based on the information given by the human. Now, what we have in the lab is, again, it's similar a little bit to what I presented before, is this notion that we can learn a representation of the shape of the object from tactile signature. Once we have the shape of the object, what we can do is project onto a given shape, as we show here, this model of moving along a line, and this line now is on the manifold of this object, and do rotation. It's very similar to the example I showed when I was having the finger jump across the shape. Now we can project this system to move along this shape, which here represents the forearm. So the green line represents this linear dynamic system, and that this is thrust along the arm, and you see that the blue one is the actual limit cycle on it. And superposed to that, we can control also for the pressure. So when we superpose these three systems projected onto this shape, we can now control specifically for both the kinematic of the motion as well as the pressure. We implemented that on the same hand as you've seen before, which is the Allegro hand, and I'll play both of them here. So observe there you have the desired force and the estimated force. So we can control for the change of the force at the finger, which matches to a large extent the profile of increase, decrease, increase, decrease, and you see this oscillation. But also, and that's the strength of the lab, which really like to talk about is you see how robust we are to change in a position. So all our control is always relative to something. So here is relative to the frame of reference of the arm. So because we project everything on this manifold, and this manifold is in the local frame of reference of the arm, then we can have this very nice linear and rotational motion with the force pattern, but relative to the arm. So we can rotate this, and we're still preserving that. Of course, this is also combined with compliant controls, so at all time you can remove that. This was, of course, a request by Samsung. It wanted this to be safe, so you should be able at all time to push the robots massaging you, just in case you're not happy with the contact that it's making. And lastly, it's a short highlight, and I know I'm jumping across many different topics, so I do apologize if it's a little too much, but I hope some of it will be interesting to you. So the last part of work that we're doing on tactile sensing these days is to try to understand how tactile information is learned in humans. And when I say tactile information, how do you as a human manage to go beyond how precisely you can perceive your the force at your fingertip? So we live in Switzerland. So in Switzerland, we have lots of watchmakers. And one thing that is absolutely fascinating with watchmaking is that the element that you have control are extremely small, and the forces are extremely small as well. I mean, it's usually 10⁻² or 10⁻³ Newton. And if you try to do it yourself, usually you won't sense anything the first time you do it. And over years of practice, these watchmakers learn to perceive this force. So we're really wondering how they would actually do that. And we looked at this particular task, which is to insert these different little screw and different positioning of this plate, for instance, on the watch. And to do that, we monitored how they will do this very precisely. So we had tactile sensors here at the fingertip, we had force torque sensors on the watch, and we had a lot of other tools to visualize the motion of the finger. So here we have the reconstruction of the position of the finger, and we also have the tactile signature. With the reconstruction of the position of the finger that we are reconstructing from camera, we can then map the tactile signature to a particular position also on the particular tool. Now, looking at the tactile signature, what we wanted to see is how this tactile signature changes across experts and novices, and whether this relates also to the force that is applied. So it's just a heads up. So what we observe is there are clear differences between tactile signature that is applied by the novices and experts. Interestingly enough, the experts actually apply much more force than the novices, but on certain areas, which are highlighted here. So it's typically on the right thumb, because they know that they need to stabilize the object, and they also apply it at different locations on the tool. So we're currently analyzing this and also using this to to control robots that could probably do similar. With that, I want to stop here and thank, of course, all the people who did the work behind this. So Meow has done a lot of work on the stabilizing of the object, and especially on having a finger that jumps and restabilize the object online. Nicola was a person who worked on this automatic adaptation to the shape of the object and maximizing the contact. Brenna and Eric did the very early work on restabilizing the object in hand, and Jason did some work on the EMG control. And then lastly, Klampeng and Ilaria are working on this watch project that I just mentioned. Okay, so I'll stop sharing here, and I can see that there are hands raised for questions. Shall I take them? Or
yep. Thank you, Professor Billard. Yep. Very impressive talk. And I was also very inspired, and I have done a lot of screw tightening after Bottle House last year. Okay, so let's go for the questions. I think Caspar has raised his hand. Shall we go to Caspar for the question first?
Thank you, but I think Sek Wang was before me, so after him.
Yeah, thank you.
Okay, can you hear me? Okay, good. Thank you for your very nice talk. So you showed a slide where three robot fingertips are holding a plastic cup, a transparent plastic cup, where the third fingertip make a slip. At that time, that fingertip tried to increase the stiffness from my understanding. So how did you make the slip detection or the state detection system? Can you explain more about that?
Yes. Actually, I have. I can show you. Maybe it's easier if.
Right.
If I show you additional slide that I removed in the interest of time. Let me just share that once more. Sharing screen. Assuming that we have a bit of time, huh? You tell me if this is not the case, Sean. Oh. All right, here we go. Can you see that? Okay, so yeah. What I did not describe for that particular work first is that we put ourselves in the frame of reference of the object, okay, and we assume that we had this model. That means that we can represent the stiffness, the rest length, and tactile data, and we can infer from the stiffness model where the center of mass of the object is. So in other words, you get a tactile signature. You get a tactile signature here, and then you infer that you infer that the center of mass is going to be where these sum with some notion of the length. Here is the rest length, so it's like a spring, and a certain stiffness parameter will stabilize the object. So that's what you start with. You assume that you're going to have a system like this to hold the object. It's simply a spring system, and you hold this with a spring. And then you get demonstration for this, the same as what I presented before. So you get this tactile signature here, which is given by this sensor. It comes from, these are the biotac sensor. They allow you to measure both the normal force, but also the tangential force. That's very useful. So you have the tactile signature here in terms of the force and tangential forces. With this, you can then represent this manifold, of course, a schematic of the rest length, stiffness, and tactile data that are stable. And once you have this, then you can retrieve the expected stiffness. So when someone pushes the object, for instance, you can retrieve what's the right stiffness to stabilize this before you actually drop the object. And this will be entirely onto what has been represented here. So for instance, in this example, the robot will refuse to rotate. Because it's been taught only to allow for translation, but not for rotation. So it's very stiff if you're trying to rotate, but otherwise not. And so this is what we use, and I'll stop here again, the sharing. This is what we use to restabilize. So in that you have it finger by finger, because this representation is for, the rest length is for every single finger, the stiffness is for every single finger. So if one is not within the manifold of what is stable, then you will retrieve the information for that particular finger. But this finger is linked to the other because you have the sum of the K times the difference of the rest length, all of them to stabilize the object.
Great. Thank you very much.
Yeah, yeah, thanks for the fantastic talk. I can only repeat that. Really impressive. And I'm always so impressed about the many things happening at your place. Definitely. So I mean, I have many questions, but possibly we cannot take them all. You mentioned adhesive approaches, so where you have some adhesive on the fingertip to improve the way to handle certain objects. And I think that's a fantastic idea. And I think we should look into that more. But you said you wanted to combine that with a tactile sensor. Why? What do you want to achieve there? Because I thought maybe have some adhesive there and job done.
No, so the ideal would have been, and I know other people have followed that. I think Metin followed that, and also there is a group in Berkeley who did that in the end. We did a very, very simple version of that. So the problem when you put the adhesive is that you lose the tactile information. So it's an either or, and that's absurd, right? The ideal would have been to and apparently it's a system that geckos have, that they do have strip of tactile sensors and strip of sort of adhesive, as if a layer mechanism like this. So we try to have that to still preserve some of the tactile information. The problem is that you had to shut down some of the tactile, right? Those that are covered by the strip and those that aren't. So that was very early thing that we tried to do, was to learn that. So basically when it's not in contact, then okay, all the strip in contact should just be cancelled. Probably similar to what the brain is doing, similar to, I mean, all the concept that you've presented, China, very interesting. It's like the attentional mechanism. If you're always in contact, then you just shut this down. So this is all what we did, was to say, we still need to have this tactile information because I'm never sure that I'm actually in contact. And the ideal would be to have this strip-like mechanism. We did not manage to do it also because it's not our strength, it's really material science. But I think there is, I need to look it up, but I think there are 2 recent publications or a couple of years ago, people who managed to do this mechanically, and I think it's beautiful. So we may want to have more of that in robotics, because it would be awesome, right, to have both, you know, sticking mechanism also here on the side of the finger, as well as the preservation of the tactile information.
Yeah, I totally agree. I have more questions, but I think I have to shut up and let others also ask their questions. We can maybe talk offline at some point. Yeah, thanks.
Sure, happy to answer also some question in the chat. I can see for a little more, but unfortunately I will have to leave for another meeting. Happy to answer on the chat as well.
We have another one raising up the hand, Tito. Are you here?
Yeah. So my question is, you have some interesting work on sensing how humans perform tasks, and the goal is to transfer the skills onto the robot. Do you have any ideas how to get the essence out of the actions that the humans do? And so how do you plan to do the skill transfer?
So it's a fairly broad question. The very first work that I showed was directly a transfer of the human skill, in other words, but it wasn't so much skill. It was more like the human knows that there are some region. If I take an object, I don't know if you see it, there are some regions that are acceptable. This is a bottle filled with something, and now everything is stable because I'm not going to drop the liquid. But if I open the cap, then there are regions that are not feasible, so that you can learn. That's the transfer of skill. And so basically you get the human demonstrating that, and then you learn the manifold of what is acceptable or not. It's an implicit way of transferring this model that we have of what is doable and what isn't. I think we as human, we really work, that's my take on it. I think we work on feasibility as opposed to optimality in most of the cases, because we just don't have the time to optimize. We just have the time to, catch things before they fall. So that's the first transfer. On the watchmaking skill, I don't have the answer here. It's absolutely fascinating, this work. We're learning tons about how humans do it. I don't know yet how we're transferring that. My goal is to transfer not the skill of the human in watchmaking at all. It's to transfer the learning skill. It's different. How do humans learn? What do they learn? I mean, how do they manage to suddenly look at a much higher level of precision in their tactile information than we do? which is basically how do they learn to adapt their attentional process that Shan presented before. How do they choose to change the granularity of their perception and the granularity of their joint space? Because there is an infinite number of things that they could test, but no, they don't test an infinite number of things. They all fall within the same type of motion. So unfortunately, I don't have the answer. I hope we're going to have it in a couple of years. Today, I can only tell you what are the scientific questions we're addressing, but I don't have the solution.
Okay, thank you very much.
Thank you. Shall we go for a very last question? Lorenzo, can I speak for the last question?
Yeah. Thanks, Aude. The amazing presentation as usual. I'm curious to know, from your perspective, from your experience of using different tactile sensors in your applications, if you can summarize, or let's say, what you think are the most useful characteristics that you have seen, or those that you haven't seen yet.
So I would love to use the gel that Chan presented. I think it would be very useful. We don't have that. So we use 3 different types of tactile sensor extensively only. The TechScan, which are capacitive, gives you only the normal force, very high resolution. So in that sense, very good, reliable, but breaks. I mean, pros and cons. Level of breakage, the fact that these sensors are not stretchable, they're not foldable, that's a limitation. I know there are a lot of people working on that. Then we have the PPS sensor. These are the gloves that I showed before that we're using. So they have the other property, they're flexible, not really stretchable, but they're flexible. But the resolution is very low. You really essentially have contact versus no contact. Well, contact, I mean, you do have the resolution of the contacts, very good, but you don't have the spatial resolution. And then we have the biotech, very high resolution. Getting the tangential force is a little of a struggle for those of you who use that. It's always difficult. They leak. I think it's awesome technology. All of them are awesome technology. I wish we would have something that combines all 3 of them. So if anyone is developing that, I'm buying for sure. Yeah, but touchable sensor is required. And thanks so much for the question, Lorenzo, because where is the problem for robots? Is here, right? It's at the knuckle. Is where you may clamp, the finger of someone. And there we can not use force torque sensor. There is no alternative. We need tactile sensing, and we need those to stretch and to be able to be very precise. So that's where I believe we need new sensors, new tactile sensors. And I know that Gordon is doing tons, so I look forward to see what he's done in this area and if we can buy any of his sensor. And you, Lorenzo, I know you also do a lot of work there, so I may not have caught up with all the new advances there. But right. I'd be curious also to have your opinion. Where do you think we're lacking? If we have time, I don't know.
Well, yeah, no, I mean, I don't know. Maybe I will say a couple of things in my talk as well. I think because I saw also in one of your video when you were doing the tactile exploration, the folding of the finger, you had the object fixed on the environment. So for me, let's say one thing that I have tried always to optimize in our sensor is the sensitivity to be able to get a low amount of force with good accuracy. But yeah, of course, it will be good to have all the properties that we need in one sensor, and probably it's not easy. I mean, it is not easy.
No, you're right. Indeed, I did not even mention that is the fact that you have to press a lot in order to get some information. That's counterintuitive because you don't want to displace the object. Yes. Okay,
but thanks. Very interesting to get your opinion.
Yeah. Thanks a lot for the feedback.
Okay, thank you for all the great discussions. I'm afraid we have to move on. And so we have this gathered town space. If Professor Billard has time, so we can have like virtual social interactions there. And also, I see there are some questions in the chat box. So please, Professor Billard, so if you have time, so please check out the questions in the chat box. Thank you. Again, thank you for a great talk. Okay, so we will